Good morning. Welcome to another session on cryptography, network security and cyber law. This is module 3, session 9 of key management, authentication, IPSEC and security at transport layer. Now in this session 9, we will be discussing about IP security. In particular, we will be discussing about the Internet Key Exchange Protocol. Followed by that, we'll be discussing about the various security policies involved in implementing IP security, and also we will see the variants of virtual private networks. At the end of the session, you'll be able to describe Internet Key Exchange Protocol, and also you will be able to see this security policy impact on IP security and explain the variants of virtual private networks. Now let's start with our Internet Key Exchange Protocol. Now the main goal of Internet Key Exchange Protocol is to establish a security association between two communicating parties using IP security. Now we have seen in the previous session as to what we mean by a security association and how it is helpful in providing security. Now this security association includes information about specific cryptographic algorithms used by that particular security association, and also it includes information on keys used for encryption and integrity protection. Now recall that IP security is provided at the network layer, and whereas the Internet Key Exchange Protocol is provided to us at the application layer. This is an application layer protocol which makes use of UDP protocol, or it is built upon UDP protocol, and it works on port number 500, and it is in turn based on two protocols or two security protocols. One is ISA-KMP and Oakley. Now what is this ISA-KMP? It is Internet Security Association and Key Management Protocol. This protocol is responsible for defining formats for digital signature and digital certificates. This is certificates, digital signatures and digital certificates. And also it specifies the rules for attaching the payload to form valid messages. Now what is this Oakley? And what is its contribution to Internet Key Exchange Protocol? Now Oakley is another security protocol which is responsible for specifying the kind of information that can be exchanged as a part of IKE. The kind of information that can be exchanged as a part of IKE is specified by Oakley. Now Internet Key Exchange Protocol comprises of two phases. Now in the phase 1, an security association is established, and also the long-term keys are derived, and since the long-term keys are derived and it is computationally exhausting, this phase 1 is very computationally expensive phase as compared to that of phase 2. Now what do we do in case of phase 2 of an IKE protocol? In the phase 2 of an IKE protocol, short-term keys are derived, and these keys are derived from the long-term keys, and these short-term keys are used by the communicating parties in order to perform further encryption. Now let's move on to the next slide. Now the Internet Key Exchange Protocol is based on the usage of Diffie-Hellman key exchange for key agreement. Now we are all aware that Diffie-Hellman key exchange is susceptible to man-in-the-middle attack and the DOS attack. Now also the attacker can induce its victim to compute useless modular exponentiation, which leads to the DOS attack. Now if too many resources are utilized, in that case the functioning of the system will be difficult. Now over here we can see that IKE is able to combat these particular attacks. That means it is able to withstand the man in the middle attack of the Diffie-Hellman, and also it is able to combat the DOS attack. Now, in order to combat these attacks, we will see what are the precautionary measures taken by the IKE protocol. Now, in the IKE, there is a choice of cryptographic algorithms that can be provided, and also authentication methods. The users who wish to communicate, they will choose what cryptographic algorithm they want to use and what authentication algorithms they want to use in order to have secure communication. Now, also this algorithm or this protocol uses cookies to subdue the DOS attacks. There are two cookies that are used, one at the sender end and the other at the receiver end. Now, let's look at the phase 1 of IKE protocol. Now, this protocol is mainly based on the Diffie-Hellman key exchanged. We all are aware that Diffie-Hellman key exchange involves extensive computation of intense modular operations, exponentiation operations. Now, we can use this in order to launch the DOS attacks, wherein the attacker creates many spurious messages. Now, each of these spurious messages which are created by the attacker will have spoofed IP addresses. Now these spoofed IP address based messages are used or they are shooted to the responder B, who will to whom they will request for setting up an IKE secure association. Now, what does the responder do when it receives such a message? The responder is not able to realize that these messages are spurious in nature, which contain spoofed IP address, but in turn it generates the Diffie-Hellman partial keys, which is used further to exchange the secret information. Now, when multiple spurious messages or many spurious messages are shooted by the attacker to the responder B, in that case every time B keeps on generating the Diffie-Hellman partial keys will lead to the exhaustion of computational resources. Now, cookies are again new entities that are used in case of this particular IKE protocol. Now, we have already told that cookies are used in order to combat the DOS attacks. Now, how do we calculate a cookie? A cookie is usually computed both the communicating parties. Over here we have taken the example of cookie being computed by a responder B. Over here the cookie is computed as a hash function of the IP address of the initiator, that is A, and a temporary secret known only to B, and also the timestamp. Now, the size of the cookie that is generated by hashing all these variables or parameters is around 64-bit, and it is integer value. Now, A will receive this cookie from B, and every time A wants to communicate with B, it has to send this cookie to B. Upon receipt of this message from A, what will B do? B will check to see if the cookie corresponds to A's IP address, or if this fails, B will simply abort the session establishment, that is IKE session association establishment. Now, in the phase 1, the following components have to be accomplished, and what are those? First is negotiation of authentication method that is to be used between the two communicating parties, and the encryption algorithm, hash algorithm, and the Diffie-Hellman group, which will be used for the key generations, are negotiated in the phase 1. Now, both the parties authenticate themselves to each other during the phase 1, and there are keys computed. Key A and key E are computed. These keys are used for message integrity and message encryption in both the phases, that is phase 1 and phase 2. And also in the phase 1, cookies are created, one for the initiator A and another for the responder B. Now, this particular IKE algorithm has two modes of operation. One mode, and specifically the phase 1 has two modes of operation. Mode 1 is called as the main mode, and this mode involves exchange of 6 messages between the initiator A and the responder B. The other mode is called as the aggressive mode, which uses only 3 messages to authenticate the initiator and the responder. Now over here we can see that the motivation for introducing the main mode is to hide the identities of the sender and the receiver from the eavesdropper. Now, having understood that the main mode has 6 messages which are exchanged between the two communicating parties, that is the initiator A and the responder B, there are 3 options of performing this phase. First option is wherein both the communicating parties share a secret key, and the second option is wherein both the communicating parties each provide private signing keys, and the third option is wherein A and B each use a private decryption keys. Now there are few notations that will be frequently used in order to understand this IKE protocol. One is CA and CB. CA and CB stands for cookies that are generated by A and B respectively. Now SA of A and SAB, these are cryptographic algorithms suite that are proposed by the communicating parties A and B respectively. Now RA and RB are already known notations to us, which represent the nonces calculated by A and B respectively. We have GA, G to the power of A and G to the power of B. These are Diffie-Hellman partial keys. Now E stands for encryption and MAC is the MAC value that is computed. Now let's have a look at the main mode and option 1 within this particular main mode. Now the 6 messages exchanged between A and B can be viewed as M1, which is shared from A to B, M2 B to A, M3 A to B, and M4 B to A, M5 A to B, and again M6 is a reply from B to A. Now let's see what exactly each of these messages refer to. The M1 is a message which is sent from A to B, and this message contains the C information on the cookie generated by A, that is represented as CA, and SAA is a cryptographic algorithm which is proposed by A for use in the IKE security association. Now remember, after having received this message 1, B needs to respond to A with the message which contains the cookie which is received from in the message 1 along with its own cookie, that is the cookie of B, and then the set of cryptographic algorithms that B has accepted, which is represented as SA of B. Now all these 3 parameters are sent back to A in message 2. Upon receiving this message, A again generates a message M3. Now let's see what does this M3 message contains. Now this M3 message contains the information of the cookie of A and then cookie of B, along with that the Diffie-Hellman partial key, which is represented as G to the power of A, and RA is a random nonce which is generated by A. Similarly, we can see that M4 is the reply which is composed by B and sent to A upon receiving the message M3. Now this message M4 contains the cookies of both the communicating parties A and B, along with the Diffie-Hellman partial key G to the power of B, and then RB, a nonce generated by responder B. Now once the message 4 is sent to A, there will be a calculation of hierarchy of keys which will be used for message 5 and message 6. Now first, before moving on to message 5 and message 6, let's have a look at the key generation information. Now IKE derives hierarchy of keys called as key R, key D, key A and key E. Now the subscripts over here that are used R, D, A and E denote R denotes the root, D denotes the derived, A denotes authentication, E denotes encryption respectively. That means this is a root key, this is a derived key, key A stands for authentication key and key E stands for encryption key. Now over here we can see that there are root keys that are derived, and also there is a root keys that are computed, and there is a derived key and authentication key and encryption key, and also we can see that MAC value is computed for the party A and the communicating party B. Now let us look at the keys or root keys that are derived. Now over here this key R represents the root key. This is equal to PRF. PRF is a pre-random function that is applied over S and also RA and RB. Now what is this S? S is a pre-shared secret between the communicating parties A and B. RA is the random nonce generated by A and RB is the random nonce generated by B. Now a key which is used as a root key in case of option 1 of using a pre-shared secret, this is the way the root key is calculated. Now the calculation of root key when using a private signature key is a little bit different. Over here a pre-random function is applied over the nonce generated by A and generated by B, along with that over a parameter called g raised to AB. This is a Diffie-Hellman parameter. Now similarly, when using option 3 wherein we are using a private encryption key, even in that case the generation of root key is different as compared to the other options. Now over here a pre-random function is applied over the two nonces and the two cookies. Now the expressions for this particular root keys are different based on the authentication method that is used. Now when we look at the generation of the derived keys and the authentication keys and the encryption keys, all of them use same expressions in order to compute the keys. Now that is applying a pre-random function over the root key and also over the parameters like cookies and the partial parameters of Diffie-Hellman, and this 0, 1, 2 specifies the options. Now over here in the last part we can see that there is a calculation of MAC address A and MAC address B. Now in both the cases A and B use MAC for authentication and integrity. Now these are denoted by MAC A and MAC B, and this MAC A is used in message 5 and MAC B is used in message 6. Now the key that is used in the computation of MAC is key A. Okay. Key A is the authentication key and it is a function of the shared key S. Okay. And this shared key is a key that is shared between the communicating parties A and B. Now MAC A and MAC B computation also involves another entity called as SAA. Now this is a cipher suite which is proposed by the initiator A. Now why is this included? Now this inclusion in the hash will detect possible substitution by an attacker of a stronger cryptographic suite by a weaker one. The attacker tends to decrease the strength of this particular algorithm or this particular protocol by replacing stronger cryptographic algorithms with the weaker ones. Now that can be avoided by including the cryptographic algorithms which the initiator has agreed on. This is also included in case of MAC. And we can also see that the MAC A or MAC B includes the identities of their sides. Now having understood all the keys and the generation of MAC, let us get back to our previous diagram. Over here we can see that in case of message 5, which is exchanged between A to B in the main mode of option 1, we can see that A is sending the cookies cookies for A and B. Along with that, it is encrypting the identity of A along with the information, that is MAC A, which it has computed over here after step 4. Fine. Now this identity along with the MAC A is encrypted using the key KE. KE is a secret key, is an encryption key which is a function of the secret key shared between A and B. Now why do we use this key? Only this key is known only to the communicating parties and only they can decrypt it. No others will be able to decrypt this particular information. Now similarly, when B receives M5 with an information of MAC and identity encrypted using KE, it responds back with both the cookies along with the identity of itself, that is B, and the MAC it has calculated, and all of this information again we can see that it is encrypted using key KE. Now this is all about what happens in main mode of phase 1 with option 1, that is option 1 is using pre-shared secret. Now the communication the communication mechanism in both the other options, that is option 2 and option 3 of the main mode of the phase 1 of IKE protocol are also similar to that of option 1. Now let us have a look over here. Now again 6 messages are communicated when we communicated even in option 2. Now the first 4 messages over here we can see they are same as that of option 1. Now the only change that we observe is after the calculation of the keys. Now in M5, which is a message sent from A to B, the cookies are involved. Along with that, a signature of A is included and the certificate for A is included along with the identity of the initiator A. All of this is again encrypted using the key KE. Now this key KE over here we can see that it is an encryption key. Now having received this message, what does the responder do? The responder B will generate a message or a reply and respond back to A. Now in response, it will send the signature and its certificate along with its identity in an encrypted form. Now this is what happens in case of phase 1 of option 2, wherein we are using private signature key in order to perform the secure communication. Now let us see what happens in case of an IKE protocol phase 1 for option 3 of main mode. Now this is little bit different as compared to option 1 and option 2. The first 2 messages remain same as that of option 1 and option 2. But what happens after message 2 is communicated by B back to A is there is a computation of hash that occurs and along with the exchange of identities. Now in this case, both sides exchange their identities in message M3 and M4. Now each side also generates a nonce RA and RB, and these nonces are encrypted with the other side's public key. we can see that the nonce RA is encrypted using B's public key and nonce RB is encrypted using A's public key. Now, each side also encrypts its identity along with the Diffie-Hellman partial key with the temporary keys Ka and Kb. Now, the Ka and Kb are functions of their nonces. Okay, over here we can see that Ka and Kb are functions of their nonces and also their cookies which are hashed. Now, in the message 5 and 6, each side transmits MAC. The MAC key is the key Ka. This is again encrypted using key Ka. Now, this key is a function of two nonces Ra and Rb. Now, if A and B are unable to decrypt with their private key, then the nonce generated by the other side, it won't be able to calculate the correct MAC. An incorrect MAC suggests that if it is detected by any of the communicating party, in that case the IKE exchange will be aborted. Now, let us see what happens in IKE aggressive mode. Now, the aggressive mode involves communication of only 3 messages between the two communicating parties, as a contrast to the previous main mode wherein 6 messages were exchanged. Now, let us have a look at the figure which contains two identities who are exchanging messages, and we can see that the messages 1 and 2 are sent in clear. Now, another aspect of IKE phase 1 in aggressive mode is the Diffie-Hellman group that is used, and the group parameters are only decided by A. Now, A computes its partial keys and sends it to B in message 1, but B has no choice of selecting its own keys, but it has to accept the group that is chosen by A. Now, let us look at the aggressive mode option 1. Now, there are just 3 messages that are exchanged between the communicating parties A and B. The first message is M1, which is generated by A and sent to B. In response, B sends M2, and in response to M2, A sends back M3. Now, over here let us see what are the parameters that are sent along with in these messages. Now, the M1 includes the cookie which is generated by A, and also the cryptographic algorithms and parameters selected by suite that is selected by the communicating party A, the Diffie-Hellman key parameters or the partial key of Diffie-Hellman, the random nonce and the identity are all sent in clear to B. They are not encrypted or anything, they are just sent as it is to B. Now, upon receiving this, what does B do? B will respond with the cookies along with the cryptographic parameters it can accept, and the partial Diffie-Hellman key, the random nonce, and then identity of B along with the another parameter, that is MAC of B. Now, M3 is the response which has to be generated by A when it receives the message M2. Now, what does this M3 message contain? It contains the cookies along with the MAC which is received in M2. Now, this is how aggressive mode of option 1 works. Now, let us see how it is different from that of how option 2 is different from that of option 1. Now, the message 1 remains same over here, and the message 2 has a slight difference, wherein in the previous case a MAC information MAC computed was sent by B to A. Over here B sends its signature along with the certificate, and these are returned back by A along with its signature and certificate, which can be used by B to authenticate. Now, next is option 3 for aggressive mode. Even in this case, we can see that the message 1, 2 and 3 differ slightly from that of option 1 and 2. Now, what happens in case of message 1 is that the message includes or the initiator includes its cookie its cryptographic parameters and algorithms it has agreed on, and the random nonce array which is encrypted using B's public key, that is the responder's public key, and also the Diffie-Hellman parameter along with its identity which is encrypted using key Ka. Similarly, upon receiving this message, B will respond back to A with the cookies and the key and the cryptographic parameters it can accept, and also RB is a nonce which is generated by B and encrypted using the public key of A. Along we can also see that B sends the Diffie-Hellman partial key and its identity both encrypted using key KB, and MAC A is also sent back to A which is encrypted using key K. Now, similarly, A responds back to B with MAC B which is encrypted using key K. Now, let us see what happens in IKE phase 2. Now, over here in case of IKE phase 2, there are again 3 messages that are exchanged. We can see it includes cookies, and there is a new term that is included here which is called as MID. MID stands for message ID, and SAA stands for the cryptographic parameters and algorithms accepted upon. Over here in this phase 2, we represent nonces with NA and NB notations, and G raised to X and G raised to Y, and all those represent the Diffie-Hellman parameters. ID of A and ID of B represents the identity of the communicating parties. MAC 1 and MAC 2 and MAC 3 are used to represent the MAC values. Now, let us see what happens in case of IKE phase 2. Now, under the existing IKE security association, if we try to establish a new IPSEC association, that is within the IKE security association, we are trying to establish a new IPSEC association. In that, this is what happens in case of IKE phase 2. Now, either party can initiate the process of setting up a new IPSEC security association under this IKE security association. Now, what happens is both communicating parties need to agree upon a cipher suite and the keys that are used that comprise the new IPSEC security association. Now, there are 3 messages exchanged in this particular phase. All the messages are encrypted using the secret key E, that is encryption key, which are computed in the phase 1, and also we use HMAC, which is helping us with message integrity and authentication. Now, for this we are using key A, that is the authentication key, which is also computed in phase 1. And there is a 32-bit message ID that is represented as MID, which is used to distinguish that this is a phase 2, because there could be multiple initiators who could be sending multiple messages for establishment of IKE security association. Now, now what is the initiator doing? The initiator is trying to establish a IPSEC association, security association. Within this IKE association, we need to differentiate between the 2 requests, right? In that, hence we use this message ID in order to differentiate between the 2 requests. Now, when message ID is included in a request, it means that the initiator is asking for establishment of a IPSEC security association. Now, the message ID along with the 2 cookies CA and CB, which are created in the phase 1, are dispatched as part of each of the 3 messages. Now, you can see this diagram. Now, cookies along with the message ID are sent in all the 3 messages. Both the sides send their proposals for the cryptographic suite algorithms that can be used for IPSEC. So, both of them send SAA and SAB respectively in message 1 and message 2. And also they use nonces in order to guarantee the freshness. These nonces are represented by NA and NB respectively. Now, after agreeing on a cryptographic suite and agreeing on the secrets, these secrets are computed simultaneously by both the parties, which are function of the decryption keys computed in the phase 1. And also we have nonces NA and NB exchanged in this phase. Now, in order to protect the integrity of the messages, each side computes MAC messages, and we have seen that there are 3 MACs used over here. Now, these MACs include integrity protection for both nonces NA and NB. Now, the Diffie-Hellman partial secrets are also included over here. We can see that there is G raised to X and G raised to Y, and also a secret key can be used in order to secure the IPSEC secure association. Now, both the sides will then try, once all these parameters are agreed upon, then they can create an entry for this new association, which security association which is created, and they can and this entry can be made on the side, on both the sides, even the creator and also the receiving end. Now, let us move to the security policy and IPSEC after having understood the IKE protocol. Now, in case of security policy for IP security, we can see that the security policy database is used. Now, this security policy database determines whether a packet sent or received should pass through the security or it should simply bypass it. Now, such a decision is made based on the fields of IP and transport header. Now, these fields we call them as selectors. Now, these selectors include the destination IP address and also the type of transport layer upon which this particular IPSEC is working, whether it is working on a TCP or UDP, and the type of application for which we are using this particular IP security. Now, the type of application which is also indicated by transport selectors are used to index into the security policy database. Now, the output of this lookup indicates whether a security should be applied. If it has to be applied and if the packet is a part of IP traffic that already has an existing security association protocol and the port number, then the SPD returns a pointer to the security association. Now, if a security association does not exist or has expired, in that case an IKE protocol can be used to establish a security association between the sender and the receiver. Now, let us move on to understand what we mean by virtual private networks after having understood whether the security policies for IP security. Now, in case of virtual private networks, it is a network which enables the organization to communicate securely over a public network. Now, the secure virtual private network uses cryptographic techniques to provide confidentiality, authentication, and message integrity. Now, we know that confidentiality is achieved using encryption techniques. Authentication is trying to prove that the source in the message is coming from a genuine person, and also message integrity is trying to prove that the message is not altered during transit. Now, in a trusted virtual private network, customer traffic is not usually encrypted. The service provider has to guarantee the confidentiality of the traffic. Now, there are two most widely used virtual private networks. One is site-to-site virtual private network and the other one is remote access virtual network. Now, in the site-to-site virtual network, they are used to link multiple offices of an organization known as intranet. Now, the site-to-site virtual private network may be used to secure an extranet, that is a network connecting multiple business partners. Over here, this is, let's say, site to site VPN is used to connect offices within the organization, and also it is used to connect the offices of the organization with the other business partners as well. Now, in case of remote access VPNs, they help connect teleworkers to their officers. Now, usually when people work from home, they use the remote access virtual private networks. Now, we have come to the end of the module 3, and in this module, I hope you are able to learn what we mean by Internet Key Exchange Protocol and the two phases of it, and the phase 1, which contains two modes of operation, that is the main mode and the aggressive mode, and the way in which the keys are generated and used in order to establish a security association. Now, also in the phase 2, we have seen how to establish a security association which uses an IPSEC. Now, moving further, we have discussed about the security policies, whether they have to be included or not. Now, this is decided with the help of the selectors present in the headers. Now, the last topic that we discussed in the session was virtual private network, and this virtual private network, we have seen that there are two types. One is site to site virtual private network and the remote access virtual private network. Now, over here explicitly the user is not performing the encryption or anything. Now, this is guaranteed by the service provider. Now, now let's end the session. Now, if in case you have any queries, you can drop an email or you can ping me on this particular contact number. Thank you. Have a great day.